Okay, so David Perez has worked in Air Force meteorology, defense contracting, Lone Eagle Systems Incorporated as the president, Space Warp Dynamics as the president, Quantum Electrodynamics as chief engineer of space systems. He's the university adjunct at 5 colleges: meteorology, astronomy, geography, geology, earth science, and physics, and has U.S. patents pending for a space warp motor and many other devices. He has additional background in electronics, software, hardware, equipment design and fab, ham radio, and aviation. His education is AS Engineering Science from Middletown, New York, BGS Geography from the University of Nebraska at Omaha, MS in Geography from the University of Nebraska, and he was also registered as a science. He was also registered science with Battelle Memorial Research Lab in atmospheric sciences at the U.S. Army. So I want to welcome David Perez to today's call. He's going to be talking about the variable electromagnetic drive. Everyone, please welcome him here with us. And David, there you go, sir. Let me ask you to oops, sorry, wrong one. There you go.
Okay.
Wonderful. Thank you for joining us, sir. And it is all yours.
All right. All right, Quantum Electrodynamics, it's been a series of companies. Lone Eagle Systems was, as you mentioned, that was more backpack meteorology for the Army, to bring it out into the field, bring weather instant, well, within a 20-minute time span to build weather products and that to the field. And the Space Warp Dynamics is was the originator of the field effect of what we refer to as the putting 2 arrays together, mimicking basically it's a thunderstorm. And how this all started was looking at Miguel Alcubierre, and according to general relativity, any type of matter or energy bends space-time. And we can observe this as for actual experiments from the 1919 editing experiment, where they photographed a star behind the limb of the sun during the eclipse. The star was appeared on the photographic evidence. We've seen other examples of this. The gravity B experiment in space also validates the fact that matter can bend light, but also it represents the fabric of space. And that's what we're going to be talking about today, is how to manipulate the fabric of space. Thunderstorms. Very naturally, they have been basically forming since the Earth's been formed, in essence, but the real power of a thunderstorm is immense. A typical thunderstorm, 20 degrees north latitude off Fort Lauderdale or Miami, can get up to 80,000 plus feet. As a radar operator in weather with the Air Force, I've measured storms up to that height at that latitude. And the amount of energy that these things can produce is like 10 to the 15th watts of power. And to give you kind of a reference, the small 13 kiloton atomic weapon will produce 10 to the 7th watts of power. So there's a 10 to the 8th watts power difference in the amount of energy that's created in these thunderstorms. And when they get close enough to each other, when they overlap, their electric fields overlap as well. And it can provide, in certain times of the year, certain instances, when solar winds are over 700 kilometers per second, the bidirectional flow of energy from the surface of the Earth to space and back again. When all these different parameters kind of engage each other, you can form a natural local space warp bubble. Now, is that just theoretical, or do we have actual evidence of this displacing aircraft? And we do. And what's interesting about this is that if you fly through what they refer to as the sucker hole near the freezing level of a cloud, you can be ejected and cause a linear displacement. And we have, I've got 4 examples today that we can look at. The structure of these thunderstorms really are 2 dipoles, a positive dipole on the top and an inverted dipole on the bottom. So that's plus, minus, minus, plus. And the minus characteristics are into the freezing level of the actual cloud itself. So height makes a difference. The amount of intensity, particularly oceanic thunderstorm evolution development, like variable winds aloft, are the key elements. And the girth of the cloud will extend out to 30 to, in some cases, up to 50 miles. And what happens within these clouds is this tremendous amount of energy. They also create antimatter. In 2007, it was thought possibility that clouds could have enough energy to create antimatter. By 2010, it was proven by the Fermi spacecraft, which was sent up by NASA to examine the universe to see if there were puddles of antimatter left from the early evolution of the universe. And they actually did find puddles of this antimatter out in space. However, they kept getting gamma ray residuals on the back end of the spacecraft. And they began to figure out that absolutely antimatter was being formed in thunderstorms. And it's not just a few antimatter particles or positrons, but we're talking of hundreds of thousands of these things energizing within thunderstorms all over the world, of which we have approximately 50,000 active thunderstorms at any given time. So very, very interesting. The 500,000 electron volts that's available for every positron that kicks off inside the thunderstorms. Gamma rays are emitted. Flight characteristics for the FAA have been changed at restrictions to aircraft, 20 miles, no more, as close flying in a normal aviation setting because of the gamma rays that are emitted. And this is like 70,000 gamma rays per minute that can be generated from these storms. So these puffy white little things that we see up into the sky are actually quite energetic, to say the least. Now, the positive dipole and the inverted dipole, plus, minus, minus, plus, was actually researched and verified by Earl Williams from MIT, atmospheric physicist. And this shows the actual type of current flow that you would generally see from the top, goes to the ground, and then comes back up to the bottom of the thunderstorm. So this is a lot different than you'll see in typical textbooks, but utilizing the same capability that Earl Williams had indicated, that is referred to as tripole fields. And when you cross these tripole fields, you will get this crossover of fields, which will generate a non-sustainable space warp bubble. And in this particular case, the terrestrial evidence that we have from Bruce Gernon, 1970, Lieutenant Colonel Hopkins, 1966, Arthur Godfrey, maybe some of you remembered him as an entertainer, was actually a naval pilot before he was the entertainer, and he's flown all the various naval aircraft, and we'll talk about him in a minute. Flying Officer O'Brien in World War II. So let's start out with Flying Officer O'Brien. In northern London, there was a Tiger Moth squadron that was testing out radar for aircraft in the early part of the war in 1941. He was aloft that day, late in the afternoon, 3 o'clock in the afternoon. He got caught up in a thunderstorm. And as he got sucked up by an updraft, he felt that his whole life was over at this point, that he was going to get damage on his airplane. It was out of control. And suddenly he saw a opening in the cloud. He was able to veer the aircraft off into the tunnel, and he ends up in northern England. He flies back, takes him several hours. He lands, he tells the story, and they say, don't put this in your logbook.
All right. And so Officer O'Brien relates this into a letter to his family. And we've done a number of television shows about Bermuda Triangle and warp fields, linear displacements with Bruce Gernon. And as a result, we got sent this email that tells the entire story, which was very, very interesting. Tiger Moth is a double winger aircraft, and it's an open cockpit, and it's not really frail. I mean, it's a training aircraft, but they adapted it for early development of radar during the war. So we get the letter, and here we have evidence of World War II. And undoubtedly, there's been other cases way back in history, but people just don't report things very often. Arthur Godfrey, the late 50s, has an experience going from Alaska to Japan. He knocks off like a half hour off of his flight time. He shouldn't have been there a half hour early. He went through a thunderstorm, went through the sucker hole, and the same thing happened to him. He relates this as a result of Bruce Gernon's experience in 1970, where Bruce encounters getting surrounded by thunderstorms near Bimini Island, and thunderstorms evolving in development from the surface of the ocean to well in excess of 68,000 feet. Well, he finds a sucker hole there, and he flies through it, and the hole is actually rotating, kind of like the right-hand rule here. And inside the tunnel, the clouds are rotating around like a cement mixer. And so he's got 2 thunderstorms that are close together and then form the hole up near the freezing level, which is about 10,000 feet. So he flies into this, and he starts feeling a hydroplaning of the aircraft and kind of a sense of weightlessness within the first few seconds. And then suddenly, a white ionized cloud surrounds the aircraft, and he can't see out. So he calls on the radio to approach control, and he goes, I'm over Bimini Island, but I'm blinded. I can't see anything, and my compasses are spinning. Well, the radar operator, approach control, tells him is that I don't have any aircraft over Bimini Island, but I have an aircraft over Miami Beach at 10,000 feet. And he says, that's impossible. I'm over Bimini Island. You have to have a mistake here. And they go, no, there's nothing there. Well, approach control radar rotates 4 revolutions per minute. So that's 15 seconds a sweep. He disappears and he reappears on the second sweep. And that's 108 miles distance from Bimini to where they picked him up on radar. He continues his flight. The ionized particles have left the aircraft. He flies to West Palm Beach, lands. He takes off at Andros Island at 3 o'clock in the afternoon, and he lands at West Palm Beach at 3:47. All confirmed and logged. And again, he's befuddled. His ground clock is the same as the controllers. So there's no time differential here. Something weird has happened. And so he spends nearly the rest of his life trying to resolve what actually happened in 1970. Now we put Lieutenant Colonel Frank Hopkins in there because he has a aircraft, a C-97, which is a very lumbering, kind of like a pregnant B-29, and it's a cargo version. And they also known as the KC-97. These things flying around 202, 210 miles an hour. They're not really fast. They're heavily, laden with equipment and things of this nature. They're flying from Kwajalein to Guam, and it takes 6.5 hours to get there. They fly that mission in 5 hours. And as he looks at his waypoints, an expert navigator, he was considered to be a master navigator. He's 300 miles downrange of where his last waypoint was. And they're flying into storm activity as well. So what's the same similar characteristics that these individuals had? And we can all say that it's anecdotal, nice story. And in fact, he was told not to report this upon landing, but he writes an article for the Ergus magazine in the 1960s, and it gets published. And I've investigated him, and I read his obituaries and everything. And this guy's on the up and up. The guy is just a very precise navigator. His whole life is very precise, very similar to Bruce Kernan. If the pencil's out of place, the man gets very upset when you're flying with him. Arthur Godfrey contacted Bruce because he had heard a program on radio of Bruce's experiences, and Arthur also had this similar experience. And so he wanted to get together. Unfortunately, 2 weeks before he had made contact with Bruce, he passed away. And so his publicist then conveyed the bad news to Bruce. And then Bruce eventually writes a book. And at that point, it's basically history. He annotates all the events that occurred during the flight, why he was there, how many times they had made the mission or flying from Andros to West Palm Beach. They were looking to put a resort in there. And this is a picture of an actual tiger moth, but this was used in radar research. I just wanted to kind of show that, let you know, is that this non-sustainable local space warp bubble that he gets caught up into, that's an air breathing engine. It's an open cockpit. He wasn't on oxygen, and he still maintained flight control with the aircraft, breathing the whole bit. But when he was surrounded by the bubble, it protected him from the any kind of exterior momentum or momentum from G forces of the aircraft. The crew was protected. The ground clocks or the clocks inside the aircraft were matched identically to the ground observer. So there's no time travel, no time shift, nothing of that nature. And I'm overly stating that because it's important to realize what really is going on here. Now, it took me years to figure this out. I don't believe a physicist would have figured this out, because you need to be the meteorologist and the physicist in order to put the various pieces of the pie together. And researching the cloud activity, getting back into the weather records for the time for that exact day. We have his refueling ticket. He always had, it was a A36 Beach Bonanza, carried 80 gallons of fuel, Andros Island, of where he came from West Palm Beach to Andros. There are no refueling stations. It's a grass field at that time. So what you came in with is what you leave with. Now, a 210-mile trip, that's what he has on his logbooks, and on the flight records, 75-minute flight. On this particular day, which was December 5th, a day before almost 25 years today of Flight 19, this area seems to have a lot of characteristics or like climate records that match a lot of these occurrences in the early December timeframe in this region. Is that a good thing or a bad thing? Well, we looked at this and tried to set up aircraft, a UAV, to actually go and fly into thunderstorms, into these sucker holes, to see if we could recreate the same type of scenario. Well, we had pilots lined up, we had the monies and all this other, and suddenly everybody dropped out because they were afraid that they would get caught up into this phenomena. And some people had visions of crashing into the ocean. So project was canceled. So it was then I decided to bring this in the lab. If this occurs in nature, and if thunderstorms do indeed create these warp bubbles, these natural warp bubbles, then we should be able to do this and bring it in the lab. The other convincing piece of information that we had was that he typically burns 15 gallons an hour, 180 miles per hour. Now, he had to do some maneuvering around, and it increased his trip distance to 250 miles. Typically, he will use 28 gallons of fuel round trip. He actually only used 29, and I got to correct on the date. It was December 4th, not 5th. 5th was the Flight 19, excuse me. Anyway, he had 9 extra gallons, and he's very finicky about flying, refueling. As soon as he landed, he goes and refuels. And we actually have a copy of his refueling ticket. And it actually says 29 gallons. Well, he uses 38 typically. We have other refueling tickets that verify that. So 9 gallons. Well, as that turns out, 0.78 fraction of an hour, that comes to for the 250 mile an hour, 250 miles that he traversed, it means he would have traveled 320 miles an hour from Andros to West Palm Beach. Well, the wings get structural cracks at 220 if you sustain for more than 20 minutes. So we've done all this research, we've looked at all this, and there's no real positive explanation other than eventually figured out from the 1994 when Miguel Alcubierre proposed a warp bubble, and it go from point A to B. And what's interesting about it is that everybody got on his case. They gave him nothing but a bunch of garbage. And all of us know, right? You guys are doing anti-gravity. You're messing with the magnetism and everything, fields, electrons, and all this. Well, they gave him the same kind of hassle. And his estimates for being able to create one of these things was all the energy in the universe. Well, we know that's not quite practical. Then they started to claim dark matter, dark energy, antimatter, exotic energy to actually create a warp bubble. And so you go through the list of scientists that have been working on this. And again, these are all theoreticians. They don't build anything, all right? And this is Van der Broek, Kleber, Obasi, and Sonny White, Dr. Sonny White, Eagle Works, which I think they closed that particular lab. But anyway, if any of those names are familiar, these guys have been working on space-time metrics. Same thing with Harold Puthoff, long worker, physicist in space-time metrics as well. So we move on here, and we finally determine, based on his experience in his particular case, and this is a rendition of what it looked like from his aircraft, or from his aircraft into the sucker hole, into the cloud. This is one of the proposed experiments. I built a UAV in the garage, and It's 7 by 7 feet. And this was a flying UAV that would be controlled from another aircraft. And once we found the sucker hole, we would fly the aircraft in, be stationed down at Bimini. It was a very intricate potential experiment. It would have been really neat to do, but we had to take this to the lab. And so energy can bend space-time. And according to Miguel Alcubierre, this all is very possible. And theory, granted, but I'm more of an empirical. I guess I didn't realize this particular slide came out fuzzy, but anyway, on our website, you can look at the papers that we have and all the other explanations that go with this. But essentially, it allows you to go from point A to B. Alcubierre, with the theory, being a theoretician, he didn't understand the actual practical side of this. In other words, his intent was, or his explanation, that a warp bubble would go a straight line if you engaged it, which means you compress the front part of the space-time, in this case, the fabric of space, and in the back of the craft, it begins to push or expand, and it pushes it all through relative space. But the bubble is isolated, and it protects the crew. No momentum, time stays the same as the ground observer, and then everything's hunky-dory. There's some tidal actions at the outside of the warp bubble. However, in Bruce Gernon's flight, he went in 10,000 feet and came out at 10,000 feet. If he actually traveled the straight line, he would have been in outer space. And so Alcubierre was incorrect, is that mass influences a warp bubble. So if you do go to space with a warp bubble, you have to accommodate for all the mass that is near and around you. You have to be able to compensate and have a navigation system that can also adjust to compensate for that relative action of being attracted to a larger mass. Now, when we brought this into the lab, we built an interferometer. We built a set of VHF antennas, which would then correspond to the frequencies at the freezing level of a thunderstorm. And so in this particular emulation, we then passed a laser down through the interferometer in between the VHF antennas, and the results of the fringe patterns that we got when the system was off, the fringe pattern would open, and when the system was on, it would close. So we were actually compressing a laser beam. And it was in, like 4.223 microns of compression. And this was extremely significant. This gave us our first clues that what we were dealing with was the potential reality. So we went on and did some additional experiments. We also looked at a frequency meter, and we put it into the throat of our primitive motor, and we got a redshift in the frequency from the frequencies that we obtained from other flights that we did from the television programs. I used the frequency data that I had collected inside the cloud. And with that said, building our first arrays, that we got a redshift, which is also pertinent in detecting the presence of a warp field. Now, the next thing that we did to try to get this to collect more and more evidence as we went along was what would happen if we were to put the motor against or near, and we've gotten results way beyond 140 centimeters. But to start off, we were 50 centimeters away from this torsion bar, which had no metal. It's a non-ferrous wood material. And we have a small little mirror, which has a mylar covering. We use the laser and we point it at the laser. We turn the motor on, and it was 25 watts of power, and the entire mass, which is 1.5 pounds of mass supported on this torsion bar, moved towards the motor. So the motor we developed is a pulling motor. Okay. So it doesn't thrust, it pulls. And that's what makes it very unique here. But the effects of the fabric of space goes right through solid material. And we've tested it with metal, actually trailer hitch balls, and that weighed 3.5 pounds, suspended them on a torsion bar. And we moved those as well. And we've tested at 25 watts of power, 100 watts of power, 200 watts of power. We have the video that we'll show you here in a bit. But it can actually adjust or pull matter through solid objects. Now, that's not charge, because we've been out to 140 centimeters. This is non-ferrous material. You see the wood torsion bar there. It's got a piece of fishing line, monofilament line. There's nothing in there that can cause this. It's some of the graphs that we plotted out, and trying to put a lot of these things together. But the interesting piece, no matter what we did, 25 watts or 100 watts of power, you follow the relative same curve. So the fabric of space really doesn't care what it is, whether it be ferrous or non-ferrous material. The curvature at various power levels, they're the same. Now, let's see. This is going to be a little tricky. Nothing's worked for us so far. Internet going out, headset not really good. You guys want to take a chance, or we want to wait at the end of the presentation before we do this?
You know, it's up to you, David. What do you feel the most comfortable with? I would say give it a shot if you feel up for it.
You want to take a shot? Okay.
Now, it may not play audio. I've noticed that's a Zoom thing. It depends on your setup, so it may not play audio if that's in there, but the video should come through.
My experience has been it doesn't play the audio correctly, but I'll narrate it if this works. It's getting out of it with the escape key. Well, let's just try.
Okay, yeah, go for it.
Okay, here we go. Now, these were made about this summer or was it last year or spring or something? Anyway, I don't know if we have oh yeah. Let's skip the ad here. There we go. The wonders of YouTube. You're probably not hearing anything.
Yeah, no, there's no sound. There actually is a workaround for that, but you have to shut down Zoom and install other software to do it. So.
I don't think we're going to do that today.
Yeah.
Okay. So May 17, 2021 experiment. We call this the Cavendish Experiment because it's very similar to Cavendish in his universal gravity experiment. I used to work on that as a side projects at Oswego State, but developing a new technique to measure universal gravitation. So remembering that experiment, we have components that are similar. Anyway, that's the reason why we name it Cavendish Experiment. So this is at 1.5 pounds. And so we are actually going to move here. The motor is 50 centimeters away. We're running at 200 watts. It's approximately 55 seconds. So we're looping it. And that's actually pulling 1.5. And this, and what's interesting about this versus the laser that we would have normally on there, you're seeing the actual physical movement due to the motor that was being used to pull this towards the motor. So the fabric of space actually is a, depending on how much energy that you have, it will move objects accordingly. Now they're going to go through the, let you see it naturally. I don't know if you're really interested in that because it takes time to do that. And we're trying to push on. Let me see if we can get back to our presentation. If I don't mess this up. Uh-oh. Can you still hear me, Tim?
Yeah, I can still hear you. Okay.
right.
So you're just trying to get back into the slideshow, right?
Yes.
Yeah, try so it should be your PowerPoint icon, I think, down there in the lower right. There you go.
Okay.
Perfect.
I teach online too, but usually I don't run into these kind of problems. You know what I mean? Anyway, after that experiment, there was a 4-video scene of the movement and how the lab is set up. But we'll go to this one now that we know that we can do this. Now, this one is actually the engine, drive, engine, motor, all of the above. Skip an ad. Here we go. So like I said, this has been under a number of years of development. And Kyle's going to be talking in my headset, and then it's going to wreck my train of thought. All right, so this is June 15th, 2020, 1500 watt experiment, 30 seconds. Most of all of our experiments that we do are because of the graphs that we produce, the plot data that we get, everything is consistent under the 30-second time test. And as we see comparison charts of energy generated, you're going to be quite amazed at how much power, at the small amount of power that we do use, that we can attain, like up to 15 newtons of power, 3.37 pounds. And in this particular experiment, that's exactly what you're going to see. Now we have a Faraday cage around this. We've done biologic tests and radiation tests with this, and there isn't anything that the motor puts out of any consequence. It's 1.5 microrads of radiation from the motor. And we've used lab flies in a test and gone out to the second generation of the flies after they've been exposed to over 1,000 watts of power for over a minute. And then they were traced, a control group against the actual activated flies, and everything turned out to be normal. In other words, one group loss of flies wasn't any greater than the other group. They were all pretty much the same, identical. Eating patterns were the same. And then we even went to the second generation of flies where nothing was detected. No malformations, same eating habits, the same lifestyle of the flies were maintained even out to the second generation. But we used the Faraday cage since in the beginning we didn't know about this. We wanted to protect ourselves. Now this is what the lab looks like. And you'll see Kyle standing back over here. We have multiple cameras onto the VEM drive itself. We even have a three-dimensional or 3D photo that you can actually get in and move it around and look all over the lab and watch the experiment in progress. The motor weighs approximately 1.25 pounds. The cables here are really high weight times cables, the 600 variety of thickness or semi-rigid cables that we employ on this. Now, that whole apparatus is suspended by a spring, and let's see here. It's suspended by a spring, and taking a hanging a hanging weight like you would use in the airport, you know, weigh your clothes or whatever, is in a scale, a hanging scale. Lifting it up, it's 3.37 pounds. And for that to have moved all that material takes 15 newtons of power, or 1500 watts. Now, what's interesting, a year prior to that, we had lifted 1.5 pounds of 6.26 newtons of force at 1700 watts of power, or 1800 watts of power. And we were able to actually reduce the amount of wattage with the new design of the motor down to 1500 watts and over double the weight. So we made a lot of progress in the last year. And our goal for the end of this year is to lift 10 pounds. So the actual experiment itself, power ratio to wattage, is actually exponential. And that's what's very exciting about this technology, is that, for example, like well, here's one of our latest motors, Model 18. This one's made out of aluminum. Our typical ones are made out of copper. And but each one of those, there are 4 tripole fields. So in essence, we have 4 thunderstorms mounted on the board. We're using fractal technology here, Koch curves, that are specifically tuned to the frequencies identified to the mid-levels of thunderstorms. And what we've been able to do is create in those tripole fields plus, minus, minus, plus. And on one side of the array, we have 2 sets of tripoles. On the other side of the array are another 2 sets, and one opposes the other. So the near fields actually cross on these arrays that have been built. And we've built 18 engines, each engine giving us a little bit more empirical data, and then applying that and improving. Pad spacing is critical. Everything. When you're working with VHF, I don't know if many of you work with that or know of it. VHF is extremely tricky to work with, and you got to know your stuff. We've performed hundreds and hundreds of experiments to get the proper pad spacing. And even though that we had equations to give us a predictor, it wasn't until we actually did the empirical, the real live stuff, that we were able to get this thing tuned and prepared in such a way as that the near fields could cross in a fashion that actually then pushes the compression of the fabric space down in one direction. We actually use a throttle. We have a throttle here. We also have computer control. We can turn the motor on and off for as long duration as we need, but we can actually start from 0 and then going up to the maximum force, which is 4,000 watts of power in our particular case. We're very cautious about over exercising, going immediately to 4,000 watts of power, because our linears that we use are, if you overpower too quickly, you could pop some circuits. This is all custom equipment, and this stuff costs well, let me just say thousands and thousands of dollars. You don't go to your local Kmart and go buy one of these things. Everything is custom. So we not only have software control built in, we can turn it on and off as far as software goes. We can do it from a local basis, which I do many times. On testing, we have a momentary switch, or we have a fully engaged transmit switch. And then using the pot, turning up the throttle, we have two settings, low and high. We have the timer here. And again, the software controls we use on occasion. We also have a tuner. We have works on a battery, DC, 48 volts. And it's 180 amp hour battery set that I've constructed here. Designed and built this. It's all custom again. It's all custom. Throttles are custom. The whole system is custom. There aren't any parts that you can buy anywhere. You'd have to start this out from scratch. The power curves. We've done a number of analysis with different types of engines, looking at the R² numbers here. For those of you, the closer you get to 1, the more perfect it is. And then if it's off on the predictor from the exponential curve, and that's what we've been working to improve. And we've gotten up to 0.992 on our R² values. And that was model 15, and we're working on 18 now. So a lot of questions come up like, what it's going to look like outside the windscreen of a spacecraft? Well, if you approach you go faster than light, it's going to be a milky looking screen as light is built up into the compression field in front of the craft. And chances are, my prediction is, you're not going to really see much. You're going to have to depend internally to a navigation system. Oh, look at that. A better Alcubierre matrix. Well, I guess you can't ask for everything, right? We got a fuzzy one in the beginning, and we got a nice one here. But anyway, this is what he came up with. And like I said, these don't really match what we have found. There are differences, is that the materials will go to the mass of the Earth or whatever mass is nearby. The other characteristics that we have not detected are the tidal actions outside of the warp bubble. They're pretty much non-existent. He indicated some very, very violent activity on the exterior of the warp bubble. But again, maybe we'll detect that as we go up in power. But to date, at 1500 watts for 3.37 pounds, we haven't detected any type of interference on the exterior. Now, what does this all mean? Well, in this case, we have the compression of the fabric space in front of the spacecraft, the expansion behind. What does that really look like for the motor? Well, here we are, the near field compression with the crossover of the near fields, which is a radar term actually, from the arrays. What happens is that this focal point gets elongated and it pushes down. So behind the engine, you have expansion of the fabric of space. In front of the engine, you have compression. Now, we went to a lot of trouble to actually map this. And we have the magnetic flux data, and we also have gravity data. We used a Raspberry Pi and an Adafruit sensor that had an accelerometer on it. And one of the interesting pieces about this is that we can see here is that the gravity data, which is fractional, corresponds to our magnetic flux data. And you see this bowing or the curving around, which is then the releasing of the compression of the fabric of space. Again, the empirical data of pulling the solid mass or the ball through towards the solid case so that the fabric of space does affect things right through solid materials. The redshift, but in this particular case, the important part here is gravity. We actually causing a fluctuation or fractional piece of gravity. Now this summer, and it's took a couple of months to collect the data, and we have 55 points across the, we call as the base sheet here. And we had the top sheet already done from a year previous. We used the same motor, model 15, and then we analyzed, collected all the points, and this is all done in 10 watts of power at 4 inches from the base of the motor to the top of the motor. It matches. It's beautiful. We even left in this little, you'll see like there's a mound here. We weren't going to be accused of altering any data. This what came out. Apparently we got a saturation in the sensor, and that's what it was. That's how we report it, and no apologies. So in this regard, with gravity data being shown that we can compress, well, we can also use this as artificial gravity in a spacecraft. Not only make the engines, because you can overlap warp bubbles and make bigger warp bubbles. It's really fascinating. We've already done this in the lab. We've been able to do full axial control. If you put a stronger amount of energy to the right, for example, it will pull to the strong side. And the other side, opposite, weak, goes strong, it pulls to that side as well. So we have full axial control capability with being able to manipulate warp fields. This wouldn't be any good unless you could actually manipulate the fields. The other things that we detected was that we had a thermal infrared camera. We put it at the end of the motor, similar to what you're seeing here in the first slide. And before, this is ambient temperature, and after. So we cooled the ambient air around the motor by 4.5 degrees. Now, what's interesting about this is the recent release of Navy footage of F-18 Hornet aircraft using their thermal infrared around UAPs, which is now the new name. To say UFO, you're classified as a whack. UAPs, you're okay, right? Just a little bit of trying to inject a little humor here, okay? But the overall objective is that those infrared images produce cold segments around those craft. We get the same thing. I believe that those UAPs or UFOs are actually operating with warp fields and have obviously really polished it up highly in evolving their technology to be able to go from 29,000 feet to the surface of the ocean in just a second, as radar operators have indicated. This is warp. This is exactly what warp is about. Now they're more sophisticated than what we have. We don't know if anybody else has it, if the government has it or whatever, but from a private from a private enterprise, as we are in QED, we have it, the basics, and we're learning every day, and we're applying every day to further the technology. Now, there are other EM drives that are out there. Roger Shire's drive, he has a he uses his in a cavity perspective, and he also uses a gigahertz worth of frequency. The problem with it is that the cavity heats up because of the gigahertz frequencies. This detunes it, and it really becomes ineffective. EM drives, or the electric drives, these have been used in space. They're very, very low amount of thrust on these things. Ion drives are the standard that they are using out in space. You got to remember one thing, is that these things take long periods of time to accelerate to a pertinent practical application, to get from point A to B. To go from the Earth to Pluto to 10 years. That's 5.5 hours light speed, okay? But it took them 10 years. It took 4 years to build up to 25,000 miles an hour, and then they looped it around Jupiter to give gravity assist and got it up to 50,000 miles an hour, the fastest spacecraft humans have ever designed. So the big problem with space, as I see it, it's too damn slow. And to get from point A to B to the asteroid belt, if you're going to do mining, you got to be able to make turnarounds really quick. Get the materials, bring them back, process them, either in space or on Earth. NASA's Ion Drive, let's also put this into characteristics. The Dawn spacecraft was a 0.92 or 92 millinewtons, which is, you can't even make a Kleenex blow in its thrust. It uses fuel, xenon gas, and they're susceptible to corrosion. The motors that we've developed, there is no corrosion, there's no moving parts, everything is solid state. And so the life expectancy of a device like that potentially could be in the tens of years. But until we get to space, we won't know that. So I'm not going to make big, claims here. I'm just saying is we've shown you what we've actually done to date, and they're very time consuming. It's very expensive. That's why I work 5 jobs, and to lay the cash down instead of writing. I mean, of course I have equations and everything else, but here are the comparisons of 15 newtons and the amount of time it takes to get there. In our Space Warp Dynamics drive, model 16, we were at 20 seconds and we were able to develop 1260 millinewtons of power or compression of the fabric of space. And here in our latest model, model 17, we're able to actually get to 15 newtons, lifting 3.37 pounds. Now, all of these other motors, they either use gas or they're using electrical energy, and the amount of wattage that they use, we use 1500 watts. Here's the Dawn spacecraft. This is 2100 watts of power. That's expensive on board a spacecraft. So what we're trying to do is our initial attempts to get into space will be station keeping motors, even though we have more capacity than an ion drive ever thought about. We run circles around them all, except just like a lot of the technology that all you guys are working on. And I refer guys to everybody. I'm from New York. That's how you talk. Well, whatever. No apologies. Anyway, that's what you guys are up against is people believing, not believing. We're in the same predicament because we're going against NASA. We're going against everybody else. We have something that actually works and they don't, as far as we understand. The new picture of the lab, we just got finished remodeling. It was too cramped. We ended up discarding a lot of stuff that we never used, and we streamlined it, built new benches and workstations, and we're trying to declutter and create more space. I mean, we only had 18 inches of space, to be honest with you, between the workbench and the tables that we had set up. So now we have 4.5 feet and we're creating an aisle all the way down. So model 16, just to finish up, I know I'm going over a minute or so. These are the goals of what we're trying to produce: VEM drives for satellites and future space stations, produce artificial gravity for any environment. That's kind of a real important thing. Retrofit and upgrade existing spacecraft, and or as we get more powerful aircraft, terrestrial or space, our designs are adaptable to power up and not to have to rebuild a particular device or a craft or a spacecraft. Our ultimate goal is to travel faster than light. Predictions are from Harold Puthoff is 100 times faster than light, doesn't violate anything of general relativity. I've heard concepts of 1,000 times. But to put it in perspective, even if we went 1,000 times faster than light, 1,000 light years, some of the most interesting places that we could go, 5 light years, 4.6 Proxima Centauri. If we could get faster than light, obviously we can narrow down the amount of time. But this is going to be the biggest problem that we face in our universe, or actually just in our own Milky Way. We're going to be restricted by the limitations, if there are, to how many times faster than light can you travel. And we'd like to test on that. So our idea for artificial gravity inside the spacecraft, putting our VEM drives, the smaller versions, the low power ones, to create a gravity dose. A recent magazine article that talked about life in space, human existence, and also plant life. They were talking 1.25 gravity to 2.45 gravity in a spacecraft for human existence. At 20 watts of power, we can produce 1.45 gravity dose, which is more than ample for human existence inside an inside of a spacecraft, and for plant life and whatnot. So we believe we've solved many, many problems of being able to manipulate the fabric of space, even within a space warp bubble, a larger one. You can also manipulate within there. So this is our Bluebird spacecraft that I designed. The full size is 7-passenger, 30 by 30 feet. And there would be pods on the side that would have the engines, but this is a test setup of lifting a 36-pound craft, all made of aluminum, handmade. It took me 5 years to build that. Okay. This is some of the ideas that we have. Missile technology, you know, there's a little scary stuff here. If you could deliver a warhead in a couple of seconds or a second to your enemy, that presents a lot of ethical problems, I guess, unstable power distribution around the world. Adaptability to aircraft, going out in space where we're at, we're going to be limited to the local space, which would be within 1,000 light years if we can get faster than light. Man-carrying craft, we already have the base of this constructed. We're just waiting for the rest of our hardware to evolve and miniaturize. And Bluebird 2. And that's the end.
Wonderful. David, thank you so much. So let me do this before we do anything else here. Let me see. I'm going to stop your screen sharing. Okay.
Gotcha. Yep.
And let me put this on gallery view. And everyone, please give David Perez an enormous hand for a truly in-depth presentation. David, that was wonderful. Now, I probably shouldn't mention this, but Jeremiah and Mark have both been telling me about your work for the last 9 months. They're like, you have to get him on. You have to get him on. And so I'm excited to finally have you on. They have been literally, in fact, Jeremiah was almost jumping for joy when I said, yeah, he's coming on. Kyle emailed me. So thank you for presenting for us.
My apologies for any of the technological foibles that we had here, but stuff happens.
Oh, no. I will try. I probably should have said something earlier. I always feel really guilty about interrupting people, but